Hey guys, welcome back. This is starting part 2 of chapter 18. So last week we went through sections 1 through 6. This week is 7 through 12. This is a super long chapter, so I apologize. And on top of it, it's just a lot of words and yeah, it sucks. I'm sorry. But we're picking up with 18.7, occurrence, preparation, and properties of nitrogen, and that's what we're going to be discussing. So nitrogen itself, most pure nitrogen we get from fractional distillation of liquid air. So the air is liquefied, and then you can separate the components of it out by their densities. Air is actually 78% nitrogen by volume, so nitrogen is the biggest component of air. Some properties of nitrogen. It is a colorless, odorless, and tasteless gas at room temperature. It boils at 77 Kelvin and freezes at 63. Liquid nitrogen is often used as a coolant, so it's pretty common. It's also used for freezing things like warts to get rid of them. It's generally unreactive because the nitrogens are very strongly triple bonded to each other. So generally nitrogen, again, is unreactive, but it will react with something like lithium and form lithium nitride, as well as certain transition metal complexes. It'll also react with hydrogen or oxygen in nitrogen-fixing bacteria at room temperature. So that brings us to nitrogen fixation, which is the process where organisms convert atmospheric nitrogen into biologically useful chemicals. This can also occur in the atmosphere when lightning passes through the air, causing nitrogen to react with oxygen, and then it forms some nitrogen oxides, which can then be carried down into the soil. So here's a very awful quality picture showing nitrogen fixation and some of these sources of nitrogen. You can see this at a lot higher quality on the OpenStax textbook online, or if you have a physical copy, it's a lot nicer. But yeah, so you've got your nitrogen here. Some of it comes from bacteria. You can see the cycle that's going on. The nitrogen then from nitrogen fixation going into soil, and you got some bacteria then that does nitrogen fixation with it, and makes ammonium, and so you can see just the general cycle. Some uses for nitrogen gas, and we're talking about N2 right now. Okay, so remember, nitrogen is a diatomic gas, and it's at room temperature. It is used often for preparing ammonia, which is NH3. Most other uses for it are generally due to its inactivity, so you can have an inert atmosphere. So canned foods, lunch meats, produce, and chemical reactions that need to be done in the absence of oxygen, for instance, nitrogen is very commonly used to make those atmospheres. Many reactions with nitrogen involve redox reactions, because nitrogen itself, the atom, can have oxidation states ranging from 3- upwards of 5+ in compounds. Ammonium nitrate is an example of a compound, a nitrogen compound, and it can lead to explosive reactions when heated. So this is a redox reaction, and ammonium nitrate is often used in fertilizers. And a lot of actually disasters have happened because what ends up occurring is the nitrogen in the nitrate ion oxidizes the nitrogen in the ammonium ion. And when that happens, it's very exothermic, yeah, and we can get very bad explosions and reactions. And a lot of people have lost their lives due to this reaction. Another nitrogen derivative, nitrous oxide, which is N2O, is used as an anesthetic, aka laughing gas. So it's often used like people need to get their wisdom teeth out. It's used. You see all these like funny viral videos of the things people say when they're coming off of the nitrous oxide anesthesia. This is the structure of N2O. On the left is kind of a 3D version, and on the right you can see some of the resonance structures. You either have a center nitrogen with these two double bonds, one to oxygen, one to nitrogen, but what also can happen is two of those electrons in that double bond can go over to the oxygen, and so you have this single bond of nitrogen to oxygen, and then oxygen with these three lone pairs on it. And if you remember, resonance structures, basically the actual structure is going in between these two, so it's just kind of going back and forth, those electrons moving. So now let's talk about nitric oxide, or nitrogen monoxide. This is NO. And it forms in low yields when nitrogen and oxygen gases are heated together. It can also form when lightning passes through air. Commercially, it's made by burning ammonia. In the lab, so if you're doing this for an experiment, it's often made by reducing nitric acid. So with some type of reducing agent such as copper. So we take some copper metal and we react it with nitric acid, HNO3. This gives us NO, which is our target product. And we also get this copper nitrate and water. One thing that's interesting about NO, it is the most thermally stable nitrogen oxide compound. Despite it also being the simplest known thermally stable molecule with an unpaired electron. So NO is a very interesting compound. It is commonly known as an air pollutant from internal combustion engines. So the combustion that occurs in our engines of our cars, it's not complete. So you end up getting some products due to this incomplete combustion that are not good, NO being one of them. So its structure, just to kind of draw out, we'll see it on the next slide, but you've got nitrogen with a lone pair, then it has a single unpaired electron, and then it's double bonded to oxygen with two lone pairs. Some other characteristics. At room temperature, NO exists as a colorless gas made of our diatomic molecules, so the single electron, the N double bond O. But what can also happen is when it's in its liquid and solid form, those unpaired electrons that are on the nitrogens, if you've got two molecules of it, they can actually pair up and form a dimer. And we'll look at what the dimer looks like on the next slide. And then one reaction that can happen is if you take it and you cool it in an equal mixture with nitrogen dioxide at -21 degrees Celsius, you produce dinitrogen trioxide, which only exists as a liquid or solid and will decompose very quickly when it's heated. So this is the equilibrium between NO and N2O2. N2O2 actually absorbs light and has color to it. So when you're in that liquid or solid phase is when you start to see this equilibrium happen. In the gaseous phase, it stays as the single molecules. And this is dinitrogen trioxide. And this, again, only exists in the liquid or solid states. And then you can see the structures, you can see the resonance structures as well. You can see this double bond, between this nitrogen and oxygen. It kind of goes back and forth between the two oxygens here. So the actual structure is kind of actually more of an average between those double bonds. It's kind of interesting. It's kind of shared there. That's the best way to describe resonance. So the next compound we're going to talk about is nitrogen dioxide. And this is made in a lab by taking a heavy metal nitrate and heating it, or reducing concentrated nitric acid with copper. Commercially, it's made by oxidizing nitric acid nitric oxide with air. It does contain an unpaired electron, similar to the nitrogen monoxide. But this unpaired electron, in this case, actually gives it color and causes it to be paramagnetic and allows it to undergo dimerization, which is where you have two of the molecules that come together. It can help form dinitrogen pentoxide, either pentoxide or pentaoxide. It doesn't matter. You can get rid of that A or not. And this is a white solid that is formed when you dehydrate nitric acid with phosphorus 5 oxide. This compound is very unstable at room temperature. And the reason it's here with the nitrogen dioxide is because it decomposes to dinitrogen tetroxide, which is what nitrogen dioxide dimerizes to. And then it also goes to oxygen gas. So we make this dinitrogen pentaoxide by taking P4O10, which is a solid, and reacting it with nitric acid. And that gives us this HPO3 solid and N2O. N2O5, sorry, solid. So this is one way we can make the NO2. These brown fumes here is what is NO2. So actually, if you were to take a copper penny and add some nitric acid to it, you would do this exact reaction, producing a copper nitrate solution, which is a really pretty blue color, and then making NO2 gas, which does not smell pleasant. Here are the molecular and the resonance structures for NO2. That's on the left side, and then dinitrogen tetroxide, which is the dimer version of it, is there on the right. So you can see those single electrons are able to grab onto the single electron of another molecule to form a dimer. And this is on the left, the molecular structure of dinitrogen pentoxide, and then at the right, one of the resonance structures. You can pretty much imagine the other types, basically, where these double bonds are kind of going back and forth. So next we're going to talk about some of the nitrogen oxides. We have nitrogen 3, nitrogen 4, nitrogen 5 oxides. So in the past, when we talked about like putting these oxidation states in the name, we really only talked about them for ionic compounds, but now that we're in the more advanced chemistry, sometimes you can have these covalent compounds where you have to specify the oxidation state because they can combine in different ratios. So the 3, 4, and 5 oxides of nitrogen react with water, and these form nitrogen-containing oxyacids. So when you take nitrous acid and react it with water, you can form this nitrogen 3 oxide, which is called the anhydride of nitrous acid. One thing that's interesting is there are actually no stable oxyacids that have nitrogen that's in an oxidation state of 4+. So this nitrogen 4 oxide is going to disproportionate the second you put it into water, and it's going to disproportionate if you're in cold water into a mixture of HNO2 and HNO3. But if you're at higher temperatures, it will disproportionate into HNO3 and to NO. Nitrogen 5 oxide is the anhydride of nitric acid, and then when you put it in water, it's going to produce nitric acid. These oxides have a extensive redox behavior. What's interesting is that nitric oxide, nitrous oxide resembles oxygen when it's heated with combustible substances. So it's a very strong oxidizing agent, but it will also decompose with heat into nitrogen and oxygen. And because of this, it's actually used as a better combustion supporter than air because it has a higher oxygen percentage than air does. So I thought that was a really interesting fact. So 1/3 of the gas is oxygen from this decomposition, whereas air is only 1/5 oxygen. So we can get better combustion using the decomposition products from nitrous oxide. Nitric oxide can act as either an oxidizing or a reducing agent, depending on what it's being reacted with. For instance, it can be an oxidizing agent. Here's an example, reacting it with P4 phosphorus. So we're reacting this with NO. So we're oxidizing that P4 to make P4O6. And then the nitrogen gets reduced. It can also be a reducing agent. And an example here is reacting it with chlorine gas. And so that chlorine gets reduced, and we make this one product 2ClNO. Nitrogen dioxide, also same thing as saying dinitrogen tetroxide, the dimer version, is a very good oxidizing agent. So just to give you an example reaction, we take some NO2 and gas, and we react it with some CO gas. We can oxidize that, and we get NO gas and CO2. So we've oxidized that carbon from carbon monoxide to carbon dioxide.